Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So taking this opportunity, I will first describe my research at Ohio State, and then I will focus on one specific problems, and then conclude with some thoughts about future research. Sorry. Sorry about that. Sorry, just 1 second. Okay. So what I'm presenting here is a collaborated work with Dr. Arora, Dr. Singhao, Dr. Guda, and Yang Choi. So in sensor networks, they are consisted of nodes which can sense, compute, communicate, and potentially control. For example, for the sensor node XSM, which was co-designed by OSU and Crossbow, it has 8 MHz CPU and a radio and some different types of sensors. So with their unique capabilities, sensor networks tend to enable us to observe and control the physical world. Therefore, they could have potentially a broad range of applications in science, such as ecology, in engineering, such as structural monitoring, or in our daily life, such as traffic control. So along with these opportunities, sensor networks also bring with it within several unique challenging issues. So firstly, sensor nodes tend to communicate with each other via wireless channels. But wireless communication could be dynamic and could potentially be unreliable. For example, here's some data showing how the link reliability changes as the distance between transmitter and the receiver increases. So overall, we do see a trend of as distance increases, the reliability decreases. But there is a transitional region where the reliability is unstable. For example, sometimes it goes up, sometimes goes down as distance increases. Also, if we look at one specific link, the reliability also changes temporally. So then the question here is, how do we provide reliable messaging in the presence of these dynamic and potentially unreliable channels? Yes?
Go back to the previous slide. So I'd understand. So like the picture on the left, that's many links, right? So that represents lots of different links rather than a single link showing this type of.
Yeah, so actually that's a good question. So here, this is just one instance given a sender. So the figure here is given a sender, and I look at its local neighborhood. So it's just one instance. So actually that's a good point. If we do the average, it will be a more smooth transition. But since given a deployment, if we look at each sensor, it has only one instance, one realization. That's a good point. So secondly, the resources are usually constrained in terms of, for example, in terms of bandwidth, energy, or in terms of memory. Then the challenge is, how do we design resource-efficient services in sensornet? And thirdly, applications tend to diverge in many aspects, such as quality of service requirements and traffic patterns. For example, in some instances, the data collection may be periodic or infrequent. But also we may be able to tolerate some packet loss or delay. But in some other scenarios, such as certain emergency detection scenarios, even though the events are rare, but once they occur, the report should be delivered reliably and in real time. So the question here is, how do the middleware services adapt to application properties and requirements to improve both reliability and efficiency? Also, in sensor networks, we have seen many different types of faults, including simple ones such as node link failure. Also, we have seen state corruptions. Within the sensor node, some system event can be lost. Moreover, given that these systems could be of large scale, therefore the overall probability of fault occurrence increases. And what's even worse is that the fault happening at a small area could propagate farther ahead and affect a lot of nodes far away. So the question here is, how do we provide guaranteed dependability irrespective of the scale? And so recently we have been seeing growing heterogeneity in the systems too. For example, this not only in the sensor network platforms. For example, this is an Intel iMode platform which uses Bluetooth instead of the default chipcon radio. Also, we are seeing sensor networks being integrated with some other pervasive systems, such as cell phone, also the internet. Then the question is, what is the right architecture for these integrated systems? And how do we provide end-to-end service in these systems? So in my research, I have looked at the first 4 challenges from the perspective of messaging. That is, how do we provide reliable and efficient messaging in spite of the link dynamics and varying application properties? And secondly, how do we provide scalable dependability? How to guarantee scalable dependability in these larger scale networks? So and my research thesis has been as follows. So for reliability and efficiency, I have proposed mechanisms which dynamically estimate link dynamics, link properties, and application properties, and then adapt its decision accordingly. So in this direction, I have proposed a protocol for using data to estimate link properties and then forming the routing structure. And then given a routing structure, the packet delivery could still be unreliable, especially in the presence of high traffic load, such as bursty traffic. Then the question is, how do we provide reliable and real-time data transport? So besides addressing this physics at the link level, another issue we could look at is how can we incorporate application properties into the middleware design so that the probability or the degree of in-network processing could be improved. And so for that purpose, I have proposed an algorithm which does this for messaging. And then for scalable dependability, I have proposed solutions which guarantee that a fault will be the impact of fault will be locally contained. Also, a network would stabilize quickly once faults stop occurring. So in this direction, I have studied how do we provide a stable clustering architecture in sensor networks in spite of node failure or node movement. And then for routing in generic networks, I have provided a solution for that. And then for path vector routing, which has been known to converge slowly, I have proposed solutions which guarantees optimal convergence in many scenarios. So while addressing these research issues, I was fortunate enough to be involved in building several sensornet systems. Among other things, such as systems integration, I have provided dependable messaging software for both the mode platform and the 802.11 networks of our sensornet experiments, Line in the Sand and Scale. Both projects were designed to detect, track, and classify intruders into certain field. And then when I was at Motorola, I have provided the MATE or virtual machine support for application adaptive messaging. And they were happy enough to file us a US patent. So back at school, I have co-designed the wireless networks of Kansai, which was designed to conduct both high-fidelity wireless networking experiments as well as sensing experiments at a large scale. As a side note, my messaging software are also deployed in Northrop Grumman Corporation and by those folks in their sensor networks and by organizations such as Castro Institute. So having briefly reviewed my research at school, in what follows, I will mainly focus on one piece of work, that is data-driven link estimation and routing. If time permits, I will briefly describe the problems of data transport and fault-containing routing. So first, data-driven link estimation and routing. So I started this work while preparing for Xscale, which was designed to study the scalability of both middleware and applications. It was deployed in an open field, And it consisted of a two-tier architecture. At lower tier, we have around 1,000 XSM modes and 200 Mega2 modes. And then at higher tier, we have around 200 Stargates, which uses 802.11b and runs Linux. So one core challenge of this project is the routing at the 802.11b backbone network. There are several reasons for this. On one hand, we have strict requirement on reliability, latency, and energy efficiency. On the other hand, our system is an event detection system whose traffic pattern differs from many other applications, such as data collection applications. And this would have some implications on how we design messaging softwares. Also, our previous experience has shown that existing mechanisms did not work well for us. So another challenge comes from the large scale. Not only didn't we have empirical lessons to learn from, the large scale also implies longer routing hops. Therefore, it poses more challenges to the messaging reliability and latency. So to address these issues or concerns, I started looking at why existing routing method did not work well for our previous systems, such as Align in the Sand, which is also designed for event detection applications. So one major reason it comes from the way the link estimation is performed. So in existing protocols, neighbors would exchange beacons, broadcast beacons periodically, and then they would estimate the unicast transmission properties, such as reliability, based on those of broadcast beacons. But there are several drawbacks in this approach. On one hand, the network condition experienced by the beacon messages may not apply to data traffic. This is because traffic pattern affect the link reliability or link properties because of interference. And also, then the traffic pattern could vary quickly, especially in event detection applications where when there's no event, the network is silent. But when an event happens, a huge burst of data can be generated. Therefore, decrease average reliability significantly. So another drawback comes from the difficulty of precisely estimating unicast properties while those of broadcast beacons. And this is partly due to the difficulty of modeling the temporal properties, such as correlation and variance of the wireless channel. Therefore, in many existing systems, such as ETX, temporal correlations are not considered. That is, they usually assume independent bit error or independent packet loss. So just to give an example how the impact of traffic pattern on link reliability and the impact of temporal properties on the estimation precision. So I have conducted some experiments with different interference scenarios. So it's not my purpose here to show you what each scenario is exactly. What I want to share here is the data that as the interference, if you look at a specific distance, as interference pattern changes, the reliability changes. For example, could be up to 40%. And then again, if we do not take into account the temporal properties, the link estimation could incur a significant error, especially in the transitional region. So what this implies is that beacon-based estimation may well be imprecise, therefore degenerate network performance, as we will see a little bit later. But then the question is, should we explicitly model the impact of traffic patterns and model the temporal properties? It turns out these tasks are not trivial, especially if we want to implement this later on in the mode platform. So to solve this, I have proposed a very simple solution. Basically, use data itself as a basis of link estimation to circumvent the complexity and drawbacks of beacon-based estimation. So in what follows, I will sort of describe a little bit in a little bit detail on how the link estimation and the routing is performed. First, the data-driven link estimation. Here, basically the question is how do we evaluate link properties while the data transmission itself? And what I propose is to use a MAC feedback to estimate link property. In many well-known MAC layer, such as 802.11, after data transmission, the MAC layer will give some feedback about the status of the previous transmission, such as whether it has succeeded or not, and and also how long does it take for the MAC to transmit this packet. By the way, this MAC latency does not include queuing delay. There are certain reasons for that in terms of the performance of the metric.
Which queuing delay are you referring to?
Like the queuing delay, the delay incurred in while a packet is sit in the queue, packet queue. So,
does it include the queuing delay from other packets also being transmitted in parallel by other nodes on their pairing links, or have you disabled RTS, CTS?
No. So we run the default protocol, 802.11 protocol. The only queuing delay it doesn't include is packet queuing delay from the packet at the load itself. So,
Okay, that's the only one it doesn't include.
Yeah,
Okay.
yeah. So among the parameters reported by the feedback, I propose to use MAC latency as a basis of link estimation, because MAC latency reflects the link reliability, since link reliability determines the number of retries at MAC layer, which would determine the MAC latency. Therefore, if we choose routes of lower MAC latency, we tend to use routes which are more reliable. At the same time, by reducing the end-to-end MAC latency, we could improve the network throughput too. So basically, the objective of routing would be to reduce the end-to-end MAC latency from source to destination. And that would determine how we define the routing metric and protocol. Yes? Okay. So as we said, so we want to minimize the end-to-end MAC latency from source to destination. Now, if we consider the geographic properties of a wireless network, then this could be transformed as minimize the MAC latency per unit distance to destination. Therefore, we can define the routing metric as MAC latency per unit distance to destination. Now let me use an example to show how this is calculated. Suppose we have a node A and the destination B, and the distance from A to B is dA of B, and then a neighbor R of A, whose distance to B is dR of B. Then A would first calculate the effective distance progress while R. That is, the effective distance progress if A send a packet to R and R forward the packet. And this is simply the distance between A and B minus the distance between R and B. And then A could calculate this metric LD for R as follows. Basically, MAC latency from A to R divided by this effective distance progress. And then for a node A could calculate this metric for each of its neighbors. And then it would use a greedy method algorithm, basically select the neighbor which gives the lowest expected value of LD. Yes?
Just go with that one more time.
Okay, I'm sorry.
Yeah, that works.
Okay. So basically, the routing by designing the routing metric, a node should be able to compare the relative goodness of its neighbors, right? So for each neighbor, it calculates this routing metric, and it's calculated as follows. We assume that we have geographic information available. So given source A and a destination B, which may be far apart, and their distance is measured by d of AB, and then a neighbor of R whose distance to B is DRB. By the way, maybe this is a little bit confusing. There could be very far away too, but these A and B can talk directly. And then first, it will calculate, say, if I send packet to R, how much progress I made.
So this means to get the message to B, you're going through R.
Yeah, yes. So calculate this effective progress, and then since we are interested in mic latency per unit distance to destination, we define the metric as latency divided by this progress. Yes.
So why would I want to do this? Or does this minimize the end-to-end MAC latency?
So it does not minimize, of course. It's a sort of a greedy approach. It does not necessarily give you guarantee that you'd minimize. So you try to reduce, yeah. Mm-hmm.
This is in place of, what does this replace in a protocol like ETX? What is it that ETX has that you don't need because you're doing this instead?
Let's see. Well, so ETX is using distance vector routing. So actually, I will come back. I have implemented the distance vector routing with data-driven link estimation. And so,
doesn't this mean that you don't do that here? Isn't this an alternative to distance vector?
Yes. So the one reason we use geographic routing is, on one hand, we have this information readily available to us. Secondly, by using geographic routing, we don't need to use any periodic control packets anymore. So that is the reason we use geographic routing. Of course, it's relatively orthogonal to the question of whether you use distance data-driven link estimation or beacon-based estimation.
Seems that they're interrelated in that I remember one of the problems with I remember hearing that one of the drawbacks of kind of estimating the unicast was the additional beacon load, right? Because if you have to do periodic beacons, broadcast covers more neighbors at one time.
Yeah.
And also that broadcasts tend not to suffer from they don't introduce they tend not to suffer from self-interference to the same degree because they don't have the CTS of the neighbor doesn't.
Right. So actually, there's a well-performed study on that. So in that study, the key part is whether you should do some link estimation or not. So it turns out you need to perform link estimation. The question here we're trying to answer is, if you do link estimation, how should you do it? Should you still use beacon as a basis of link estimation, or you would like to use data itself as the basis of link estimation? Yeah. Yes.
The
What?
Euclidean distances.
Pardon?
The DAB is the distance between A and B.
Yes.
You assume that information is available?
Yes. Actually, when we go, basically, when a node starts, there are some neighborhood discovery. And as a part of that process, the location of the destination is propagated. We'll see in just 1 second in detail. Yes.
So how do you say bootstrap? So you said they use data because initially they have data planned, so they don't do data estimation.
Yeah, that's a good point. Basically, when a node boots up, just in short, it would perform some initial link estimation. And we'll talk about that in detail, why we do that and why it is feasible. Okay. Yes?
I'm not quite sure why you're concerned about distance between the nodes here, when that should figure in. Let's say that you got lucky and there was some natural waveguide between two nodes that happened to be far away. So the link quality there would be really good. So but it's still you're divided by distance. So I'm not quite sure why distance is important.
I guess, so you're saying maybe some links could be, even though they're long, they could be very well, could be a good link.
Maybe you get lucky.
Yeah. Actually, that's one part which will be explored by the data-driven link estimation. But still, even in that, suppose I have two links. One is a long link, long reliable links. Another is a short reliable links. Then I would prefer using the long reliable links, right? So by that, the distance progress is larger. Yeah. So John, you have okay. So then the routing metric is basically a node would select a label which gives the lowest expected value of LD. And that's why we call the metric as ELD for expected LD. But I'm sorry, I'm not good at giving names, so please bear with me. So now let's come to the routing protocol. That is how to perform this link estimation. So again, here the objective is to use data to estimate the ELD for each neighbor, and then maintain the next hop forwarder based on their expected value of LD. So, and a node would follow the following procedure when it in this protocol. So when it boots up, it would perform some neighborhood discovery, such as basically the location of its neighbors and some IP address of its neighbors. Also, while the neighborhood discovery, the location of the destination is propagated from the destination to the rest of the network. So one part is the initial sampling. That is, when a node, yes.
So is there a single destination that's local to the network?
Oh yeah, yes. So here we are considering a converge cast. But of course, if we have multiple destinations, this same procedure.
Okay.
Yeah. So when a node discovers one neighbor, it would perform some initial estimation to get a sense of how this link, how the link is in terms of its quality. So we'll come back to this point a little bit later, seeing why this is feasible, or will not cause too much expense for us. And then after the initial boot up stage, when a node starts forwarding traffic, it would use the mic feedback to adapt its estimation of the metric for its neighbors. And then based on that, it would maintain its current forwarder based on the dynamically estimated ELDs. So we have analyzed the random sequence of LD, and it turns out that the simple estimator is good enough for us. So as a part of the link, yes?
So you say that's a simple estimator. Why are alpha and beta to the R separate parameters? Why do you allow alpha very differently from beta to R?
So actually, beta R comes from the, that's one part I had planned to speak about. Beta R is, the reason we use beta R is because of the implication of data-driven link estimation. Basically, if I have two links, link A and B, and at one point I take a sample of A while sending a packet to A. But after that, I start using link B for sending traffic and take sampling. And then after some time later, I come back to link A. Then there's a huge gap in time between this sample, the previous sample, and my current sample. So the beta basically is a factor reflecting this effect.
But is it like, okay.
Because there's variations,
So you
right?
weight the recent
Yeah.
sample.
Yeah.
So okay.
Mm-hmm. Yeah.
So you weight the recent sample highly and the old one not very.
Yeah. It's essentially that way. So as a part of the link estimation adaptation process, a node would identify those neighbors where the links are extremely unreliable, and then stop using these neighbors later on. So that's a basic routing protocol. One drawback, one issue with this basic routing protocol is uneven link sampling. Besides the issues we raised over there are some more serious issues. Basically, a link will be sampled only if it's used by the node in forwarding traffic, and this could cause some problems. Again, I will use an example to demonstrate this. So again, node A, its neighbors, it has neighbors R and R prime. Suppose currently R is a better forwarder. So A would send packet while link AR. So therefore, link AR is sampled, but the link A from A to RI is not. So the status is unknown. And then this could keep going until a point in time, say T0. And after T0, suppose link ARI becomes better. So ideally, a node, if a node knows this situation, it would send data while link ARI. But since link ARI is not sampled, so node A would not know this. Therefore, it would send packet still while the link AR. So therefore, the beta route could be missed in the routing selection process. So to address this issue, I proposed using some controlled exploratory sampling. Basically, a node would proactively sample some alternative labels with carefully controlled frequency and interval. Again, let me use an example to show how this is executed. Suppose A, a label R and some label Ri. Now, suppose A changes its forwarder to R at time T0. Then at this point, A would set a timer whose timeout value is a constant times the probability of R being the best. So suppose the timer will fail at TE without any interruption. Now if R was continuously used as a forwarder until TE, then A would execute this exploratory sampling. That is, it would sample another neighbor Ri with a probability of this neighbor being the best forwarder, and then this process could keep going. Now, suppose in another case, suppose A changes its forwarder before the timer fails. Then A will first cancel this timer, and then set another timer corresponding to RJ in the same method, and the same process would continue. So the intuition here is that if we have perfect sampling, we will just stick to the best label. But since we don't have that capability, we still, on one hand, we want to sample the alternative labels, but we want to control the frequency such that the better label would have much higher probability of being used. So that's a basic routing protocol. So, yes?
Okay. Where do the probabilities come from?
So basically, we have found that the mic latency at LD follows log-llama distribution. So given a set of neighbors, we have estimated its mean and variance, and then we calculated the probability. Yes?
My real question is how sensitive are the results to that?
Mm-hmm.
I mean, it's just check each neighbor. How much worse? How much better does this work than round robin?
Mm-hmm. You mean how much? How important is this procedure?
Yeah. No. I mean, using and tuning these probabilities. Yes, you want to check other neighbors.
Yeah. But I want to check it with controlled frequency. For example, if a neighbor is whose quality is close to my current.
Understood.
Yeah.
I guess my question. It seems like this is a lot of overhead for a relatively simple thing. Are you going to show us at some point here to
Yeah.
say,
Yeah.
Once a second, check another neighbor?
Yeah. Yes. Yeah, I'll show that in a few slides. Yes.
Can you give us an idea about how many neighbors there are to check?
So actually, this is controlled. So in our implementation and deployment, a node keeps up to 16 neighbors. 16. Yeah. So by the way, it has more labels than that, but it would control the label table size. This is especially important in the mode platform, which we are currently implementing. So one issue with this data-driven link estimation is how responsive is it? Since we are using data itself for link estimation, it has to be responsive enough. Otherwise, we may end up using the bad route. Okay, to answer this question, we have analyzed the sample size requirement. Again, we found that mic latency and LD are not normally distributed. Therefore, log of LD is normally distributed. And then, given any two links corresponding LDs, we can calculate the sample size required to compare the goodness of these two neighbors with different levels of different confidence level. So based on this formula, I have studied and sort of take a trace of a system and see how many samples are required for the node to find its best labor. And this shows the sample size distribution given different windows of comparison. So what this says is, in many cases, the sample size is very small. For example, the 75 percentile is only 2, and 80 percentile is 6. So what this implies is that in practice, the routing could converge even if we use data-driven link estimation. And secondly, it implies that by performing the initial link estimation or initial sampling, we could get a relative goodness of a sense of the relative goodness of neighbors with relatively very small sample size samples to take. Yes?
Do you assume like it doesn't change it before you actually run that initial sampling that you already
Yeah. So actually, that's another aspect where the exploratory sampling could help, because by initial sampling, the estimation may not apply exactly as a later on, but to give you a jump start, kind of as a boot up process. Yes.
Yeah, this doesn't feel like an end-to-end metric. End-to-end, I want to know that, that I am paying when I do exploratory sampling during the times that the link quality didn't change. That is justified by the gain I get from switching the times when something has changed, right? That's whereas like the definition of best neighbor seems static here. So I mean, you say 95% confidence level in this slide. Maybe 70% confidence level is the right confidence level for making changes within the appropriate period of time. And the idea of sample size, there's no time, right? It's I need 6 samples. Whereas really, it seems like what you want to do is figure out how to set that timeout value in the other slide.
So actually here the sample size is based on by window of comparison. For example, if I take a sequence expanding 1 hour, I divide it into different chunks of different chunks. For each chunk, I have a sample size.
Okay.
So basically, this sort of reflects the temporal variations to a certain extent. So for each chunk, we have a sample size requirement. Now we look at what are the distributions of the sample size requirement. And that's the data shown here. Okay. Maybe I should have mentioned that explicitly. Okay. So with that, we get more confidence this protocol could work in practice. But then the question is, could we implement it in existing platforms? It turns out it was not the case. For example, so in our case, we used Linux because of we use targets. So in existing Linux, it does not give feedback for the successful transmissions. Also, in the feedback, it does not include the information on mic latency. What's even worse is that we cannot correlate the feedback with the corresponding packet transmission in existing systems. Also, the feedback could be lost in the presence of a high traffic load and or when the node uses unreliable links. So I have to solve these technical issues, I have modified the driver and the caller to provide the feedback and to prevent the mic feedback loss. So by the way, this module has also been used at other places such as Sensory Corporation and UCLA, the MSTAR teams over there. So based on that, we can implement the protocol. Now the question is, so how does data-driven link estimation and routing perform in practice? To answer that question, we compared it with the state-of-the-art in beacon-based routing, represented by ETX, which is distance vector routing, and uses a metric for expected transmission count. And then another protocol is PRD, where the metric is product of link reliability and distance progress. This protocol is based on geographic routing. And also to understand some design decisions of loaf, we studied the performance of other versions of loaf, where, for example, there's no exploratory sampling, or we consider every neighbor in sampling, or we sample after every packet transmission or every short time or some interval. Here I only study every packet transmission. By the way, these versions are used in some other existing protocols, like sample every packet or sample every node, such thing. So another version I studied is to study the impact of the assumption of geographic uniformity. That is, in many geographic routing protocols, they usually assume that we have this uniformity across the network. That is, the network condition is similar across the network. So based on that assumption, I implemented another version and studied its performance. So we studied the performance of these protocols in our testbed Kansai, where we have around 200 802.11 devices deployed in a 15 by 13 grid. And we injected the scale traffic trace from the right bottom color to the upper left color. And for each protocol, we measure the end-to-end MAC latency because it affects the network throughput. We measure the energy efficiency. Also, we study the properties of links used in each protocol. So this figure shows a box plot for the end-to-end MAC latency. So from here, we can see that the loaf, the data-driven routing protocol, loaf, reduces the MAC latency by a factor of around 3 compared with the beacon-based routing protocol. And then compared with other versions of loaf, it also performs better. What this implies is that we should control the labor sampling carefully. Also, we should not assume geographic uniformity when designing geographic routing protocols. And then in terms of energy efficiency, of course, loaf could save some energy by not using periodic beacons. But we are showing here is the number of energy taken consumed for transmitting the unicast packet. And it's measured by the average number of unicast transmissions per packet received. So again, we can see loaf reduces the required number of transmissions by a factor of about 1.5 or 2.4. And again, compared with other protocols, it performs better. So then a little bit detail. Yes?
Okay. 5 unicast transmissions per packet received. Now, is that including multiple hops across the network, or is that, you say received, what are you dividing by?
So that includes the, yes, it's end-to-end the number of transmissions.
Okay.
Yeah.
So what are path lengths here?
Path lengths? The routing hops?
Yeah.
It's about, I think for ETX and loaf, it's about between 3 and 4. I think I have some data. If yeah, it's about, yes.
So you perform the experiment between the particular two nodes. Did you try other combinations?
Yeah. So we tried multiple sources. Also, we tried using periodic traffic instead of the scale trace. And we have some similar. So then how about the links used in each protocol? And here, what we showed is the transmission failures in each protocol and the geographic physical length of each links. So what we can see is that the beacon-based routing tend to use unreliable links, even though the length of the link is equal to the length of the link in data-driven routing, or even smaller, shorter. Basically, what this implies is even though they choose links of similar length, those links could be unreliable in beacon-based routing. So another comparison we could look at loaf and where the loaf where we don't have label sampling. So both protocols use reliable links, but loaf was able to find links which is longer than the case where there's no neighbor sampling. So basically what helps is that loaf could find those long reliable links. What this implies. So yeah. Uh-huh.
So how long is the xScale traffic trace?
At tier 2 we have some aggregation. Therefore, for each event we have 19 packets. So for each protocol we run the same, inject the same trace for 50 times, and then taking the average.
Okay, and so then the no sampling, that's no. What does no sampling exactly mean? You're not sampling? Is it not sampling at the beginning, or is it not sampling?
Sorry, yeah.
Probabilistically.
Yeah, it does the latter one.
The latter one.
Yeah.
So is it? So is what you're saying that there are? Is the performance of loop over LNS because there are temporal changes?
Yes.
So there are temporal changes during the 19 packets?
No, during the whole duration.
Okay, so so you send 1,000 packets and there are temporal changes over the 1,000 packets.
Yeah.
Okay, so when I looked at the picture, it looked like it was kind of a hanger.
Mm-hmm.
Right?
The picture back.
Yeah, the picture of your deployment.
Mm-hmm.
Why should we expect there to be temporal changes?
You mean in this scenario?
Yeah, like I don't know.
So actually, there are some intervals between each trace. I think it's about 10 minutes.
Okay.
So overall, I think that would be 10 minutes times 50, 500 minutes. 500, about
10 hours.
Yeah. And I think in that case, there may well be, if we look back at the temporal variations, there could be some slight changes. I guess another contributing factor could also be the initial estimation.
Okay.
As we mentioned, that's also one point where exploratory sampling could help.
But I thought that LNS did do the exploratory sampling at the initial, or at the very beginning of time. It does the sampling at the very beginning?
No, I'm sorry. No, it doesn't do this in the process of data transmission.
Right, it just does it once and keeps a snapshot.
Yes, and then just use a basic protocol. Yeah. So as Bodhi said, asked, we have studied other scenarios. Also, we have studied the case where suppose we don't have geographic information. That is, then we could use data-driven link estimation plus distance vector routing. And also, we have measured the network throughput. So this shows MAC latency for distance vector routing. Again, it's much better than the existing protocols. On the network goodput, by using data-driven link estimation, we can increase the goodput significantly. So this protocol and its implementation has been deployed in xScale and supported the project. And it's currently used by Northrop Grumman Corporation and also in our testbed Kansai. Can I spend 5 minutes on just 10 more minutes? Jim?
Yeah.
Okay. Okay. So then let me spend 5 minutes just by briefly describing what these problems are. So by using the routing protocol, we have a routing structure. But then this does not give us guarantee that we would have a reliable data delivery, especially in the presence of high traffic load. Then the question is, how do we transport high volume traffic reliably and in real time? To give an example how existing systems performed, I showed one case about the performance. So in many systems, in order to improve the reliability, we would retransmit the packets which are identified as lost. So what this here we show the data in terms of reliability. See, as the number of retransmissions increases, as we can see, as the number of retransmission increases, the reliability may only increase slightly, or may even decreases. And the reason is that if retransmissions are not controlled carefully, it could cause even more contention and more packet loss. And then basically the question is, the problem is how do we design a protocol which could give us about close to 100% reliability and close to optimal throughput or good put, which also implies the real-time packet delivery. And to solve this, to provide this solution, basically we need to design the mechanisms which perform some contention control so that retransmissions will not interfere with the existing transmissions. Also, to guarantee real-time packet delivery, we designed the block acknowledgement protocol, which is non-blocking in nature. So that's about the reliable and real-time. Yes.
How is it different from RTS, CTS?
So actually, so we have similar observations. If we do the same experiment by changing the contention window size, or if we use RTS, CTS, using RTS, CTS could improve the absolute reliability. For example, in our case, we got with RTS, CTS, we have around about 67 packet delivery rate. But again, even if we use RTS, CTS, as the number of retries increases, the same phenomenon still happens. So I think RTS, CTS can reduce the degree of collision, therefore improve the reliability. But then the question is still, in the presence of this extreme high traffic load, how do we control the retransmission? And how do we conduct the block acknowledgement? Yeah. So these protocols try to deal with physics, trying to either choose better route or control the retransmission so that we can recover packet delivery. So I guess another issue which is equally important is when we implement this protocol, then how do they perform when some fault happens, for example? So the question is, how do we guarantee that a fault at a local area does not propagate further beyond? Again, let me use an example to show this. So here's a state, an example of distance vector routing, where the D is a destination, and each node maintains its distance in terms of number of hops to the destination. Now suppose if the distance value of H get corrupted, instead of 2, corrupted to 1. So ideally, H should correct itself in this case. Therefore, only H itself is affected. But what may well happen in practice is that the fault state corruption at H could further propagate beyond its local neighborhood. For example, so before H corrected itself, the state corruption could have propagated to J and K. Now H may correct itself. But then before J and K correct themselves, the state corruption could further propagate to their descendants, and so on. So in the end, the network would converge, would stabilize in the end. But during the stabilization, a lot of nodes get affected. So the issue here is that if given an arbitrary network and starting at an arbitrary state where the perturbation size or the size of the perturbed region is S, how do we guarantee that first the system would stabilize, and secondly, during the stabilization, the impact of faults at this perturbed region would not propagate beyond a certain distance, depending on the perturbation size itself. And to solve this issue, basically we need to some mechanism which could automatically identify the source of propagation, and then by controlling the diffusing computation involved in these algorithms, so that faults will not propagate unboundedly. So just a brief summary and some thoughts about my future research. So in short, so my research I have looked at messaging in sensor networks, and mainly I have focused on how to deal with link dynamics and varying application properties, as well as the interaction between link dynamics and application properties. So both protocols and implementations have been verified in real-world systems. And then on fault tolerance, I looked at how to guarantee fault containment and local stabilization in these large-scale systems. And some of these concepts have been actually applied in when we implement our protocol in TinyOS, the mode platform. So currently, we are porting this data-driven link estimation and routing protocol to the mode platform. And also, we are trying to study the performance, compare its performance with some other routing metrics, which tried to take into account the impact of temporal correlations. So another piece of work we're doing is to study the validity of indoor wireless experiments. So to study why we would be able to generalize the observations in indoor to the outdoor environment. So about some of my thoughts about future research, I think one important issue is sensor network architecture. So recently we have seen effort in terms of providing different types of abstraction from the perspective of network and application. But then the question is, could these two efforts converge at some place? And if so, what would be the right interface? And how do we provide the runtime support for in-network processing and quality of service for application? And secondly, we are seeing that the sensor networks are being increasingly being integrated with other pervasive systems and the internet. Then the question is, what is the right architecture for the integrated system? And how to deal with the new network dynamics posed by some other systems, such as some cell phone. That is, how to deal with mobility or the issue of intermittent connectivity. And then how to provide end-to-end quality of service in the integrated system, given their heterogeneity. So while implementing my protocol in TinyOS, we have observed some sort of complex faults. For example, sometimes some system event may be lost. As a result, a state could be corrupted. And then it may happen that a node would just die because of that, since basically a variable which is a guard for transmitter packet, if that gets corrupted, then the node may not be able to transmit anymore. So we ended up using some techniques such as invariant checking to deal with these issues. I think in general, how to design and implement dependable systems is an important as well as a challenge for us. And I would like to spend effort in this area in terms of protocol design and the implementation, and how to provide the runtime or system support for fault detection and correction, as well as tools for monitoring and management. I guess another aspect which is equally important and interesting is the modeling to model these dynamic systems, both in terms of system dynamics itself and the method of reasoning about the system properties such as stability and composition. Of course, to that purpose, we need tools for model build-up and some performance analysis and evaluation. So with that, I conclude my talk, and here are some related references for my talk. Thank you very much for your attention.
I'm about in your fault containment from routing work.
Yeah.
What is the model for faults? Is it the general state corruption?
State corruption is one part of it. There are node failure, node join. So we have we have two pieces of work in that direction. One piece of work is any arbitrary types of fault, but the fault would stop after some time. That's a work on the distance vector routing.
Okay.
And then another piece of work is, what if in some scenarios faults may keep happening, may not even stop at all? In that case, how do we provide fault containment?
Okay. In the case that just in brief, how do you contain faults that occur temporally?
So basically.
Go ahead. I'm sorry.
So basically, all these many algorithms, including the routing, are based on diffusing computation. Right? So the reason fault can propagate is because certain diffusing computation can carry this corrupted state far away. So basically, the technique is how do we design the diffusing computation such that we could have multiple layered diffusing waves, so that if one diffusing wave is initiated incorrectly, I can use another wave to catch it and stop it.
So is it the case that you have slower convergence? And are you trying to slow down convergence in some scenario?
So theoretically, yes, because we are reducing the speed of the lowest level diffusing wave. But in practice, if we look at the implementation, even in existing systems, we have certain timers. So we use the same timer to control the lowest level diffusing computation. We just use higher, smaller timers for other waves.
Why should I trust that the first wave is the wrong one?
Yeah, that's a good question. Sometimes you may even make the wrong decision. So basically, we have 3 waves. So the second, okay, let's, we don't have. So let's say layer wave 0 is a default routing protocol. Right. And then we have layer 1, which tries to detect any mistakenly initiated waves. If some waves are detected, we would try to catch it. But then, of course, sometimes this layer 1 wave could make mistakes. And then we have another wave, layer 2 wave, which will contain this fault. And the reason we can have this approach is that the highest layer wave does not introduce any new variables at all. So therefore, it itself will not make any wrong mistakes. Even if it may make wrong decisions, it will not propagate beyond. That's a basic intuition. Thanks.